December 5th, 1944, Philippine Sea, 05:47 hours. The shell screamed upward into the pre-dawn darkness at 2,800 feet per second. Lieutenant Commander Howard Mitchell watched it climb through his binoculars from the deck of the USS Lexington, his knuckles white against the cold metal railing. 34 Japanese aircraft bore down on the carrier group, their engines a distant growing thunder. His gunners had fired 3,000 rounds in the past month, direct hits 17. The mathematics of survival were brutally simple. You needed to throw more steel into the sky than the enemy could dodge. But this shell was different. Mitchell didn't know it yet, but packed inside its nose cone, smaller than a grapefruit, was a device that would have seemed like science fiction to his father, who had manned similar guns in the First War. A miniature radar transmitter, a receiver, vacuum tubes no bigger than his thumb, components so delicate that engineers back in Washington had sworn they'd never survive the 20,000 G shock of firing. And yet, the shell detonated 40 feet from the nearest Japanese aircraft, not on impact, not on a timer. Before contact, the bomber disintegrated. Pieces of wing and fuselage tumbled toward the black water like burning leaves. Then another explosion, another aircraft gone. The remaining pilots scattered, their formation breaking like a flock of startled birds. In 70 seconds, the Americans shot down 8 planes. Mitchell lowered his binoculars, his hands trembling, not from cold, not from fear, but from the sudden vertiginous realization that he'd just witnessed the future of warfare. "Jesus Christ," whispered the young ensign beside him. "What was that?" Mitchell didn't answer. He couldn't. Because the truth that American scientists had managed to fit an entire radar system into a 5-inch shell, that they'd created a weapon that thought for itself, that hunted its target through invisible radio waves, seemed impossible even as he watched the evidence burning on the water's surface. The Japanese called it Bakemono, the monster. The Germans, when they finally captured an intact specimen, would stare at its components with a mixture of horror and disbelief, their own scientists declaring it at least 25 years ahead of anything they'd conceived. But on this December morning, as the tropical sun broke over the horizon and illuminated the wreckage of what had been an elite strike force, Lieutenant Commander Mitchell knew only one thing with absolute certainty. The old rules no longer applied. Der Sarvicum Part 2, The Desperation That Breeds Miracles. To understand how America created its secret weapon number 2, surpassed in classified importance only by the atomic bomb, you must first understand the mathematics of death in 1940. Picture an anti-aircraft gun crew in London, autumn of that year. The Luftwaffe is coming every night. The sound of aircraft engines sends hundreds of thousands into the underground. Your gun can fire 15 rounds per minute. Your shells rely on timed fuses, clockwork mechanisms set before firing. You estimate the enemy's altitude, speed, and trajectory. You guess the intersection point. You set the fuse. You fire. You pray. The statistics were merciless. British and American anti-aircraft batteries required, on average, 2,500 shells to destroy a single enemy aircraft. 2,500 shells, each one representing hours of manufacturing, pounds of brass and steel, skilled labor, transportation, each one costing in 1940 dollars approximately $8. Small change until you multiply it by the thousands of aircraft filling hostile skies. The mathematics spelled catastrophe. Merle Tuve understood this. The physicist, 40 years old in 1940, director of the Department of Terrestrial Magnetism at the Carnegie Institution, possessed one of those restless minds that refuses to accept impossible as a final answer. He'd studied under legendary physicists, worked on early radar development, and now found himself drafted into a desperate race. Could science create a better way to kill? The concept seemed absurdly simple. A shell that could sense its own proximity to a target and detonate at the optimal distance. Simple, except it required cramming radio transmitters, receivers, amplifiers, power supplies, and a detonation mechanism into a space the size of a soda can, making it all survive forces that would kill a human being instantly, and manufacturing it cheaply enough to fire thousands per hour. "We'd have better luck teaching the shells to think," one engineer muttered during an early meeting. That's essentially what they did. The Applied Physics Laboratory at Johns Hopkins University became the Manhattan Project's lesser-known sibling, smaller, quieter, but no less revolutionary. Starting in 1940, Tuve assembled a team of 800 scientists and engineers. They worked in hastily constructed buildings. They slept on cots beside their workbenches. They faced a cascade of seemingly insurmountable problems. Problem 1, vacuum tubes. The beating heart of 1940s electronics, these fragile glass structures filled with metal filaments typically required gentle handling and stable mounting. Now engineers needed versions that could withstand the shock of firing, forces equivalent to dropping a car from a 20-story building. The first test firings turned the tubes into glittering powder. Harry Diamond, an eccentric radio engineer at the National Bureau of Standards, solved it through sheer stubbornness. He developed tubes with filaments wound so tightly, supported so precisely, that they could survive the brutal acceleration. Testing meant firing prototypes into sawdust-filled barrels, digging out the fragments, examining the failures under microscopes, and trying again. And again. And again. By late 1941, they had tubes that could survive. Barely. Problem 2, power. The fuse needed electricity, enough to broadcast radio waves, receive the echoes, and trigger the detonation. Batteries of the era were too heavy, too unreliable, too prone to failure under stress. The solution came from an unexpected direction, the shell's own spin. As it rifled through the air at hundreds of rotations per second, tiny generators converted that rotation into electricity. The shell powered itself by moving. Problem 3, discrimination. The fuse needed to distinguish between genuine targets and false echoes, clouds, rain, ocean waves, the ground itself. It needed to ignore everything except enemy metal at the right distance. Engineers developed circuits that filtered signals, that recognized the Doppler shift of an approaching target, that essentially taught the shell to recognize friend from foe, real from phantom. By June 1942, they had working prototypes. By August, they'd fired successful tests against radio-controlled target drones. The drones didn't survive. By October, they'd refined manufacturing to the point where each fuse cost $20, still expensive, but affordable compared to the alternative of letting enemy aircraft through. The security classification was absolute. Workers manufactured components without knowing their purpose. Assembly line staff put together pieces without understanding the whole. The word radar never appeared in any documentation. Officially, the device was called the VT fuse, supposedly standing for variable time. In truth, it stood for nothing. The designation was deliberately meaningless, a verbal smokescreen. When the first shipments went to Navy vessels in early 1943, they came with extraordinary restrictions. Use them only over water where a dud couldn't fall into enemy hands. Use them only when enemy contact is certain. If any unexploded shells land on enemy-controlled islands, Navy demolition teams must recover or destroy them, regardless of risk. The paranoia wasn't unwarranted. Intelligence indicated that both Germany and Japan were working on similar concepts, but were years behind. Keeping that advantage required obsessive security. In the entire war, fewer than 100 people knew the complete technical details of how the proximity fuse worked. One of them was Section Chief James Van Allen, who would later discover the radiation belts bearing his name. In 1943, he was just another exhausted engineer, 30 years old, watching test after test, refinement after refinement, knowing that every improvement meant more American pilots coming home, more ships surviving kamikaze attacks, more soldiers protected from the V-1 rockets that would soon terrorize London. "We're not building a better mousetrap," Van Allen told his team during one late-night session, his eyes red from fatigue and tobacco smoke. "We're building a mousetrap that moves at the speed of sound and thinks for itself. When this works, really works, it'll be like giving every anti-aircraft gun on every ship and every battery a brain." He was right. But the true impact wouldn't become clear until American forces began facing an enemy desperate enough to turn pilots into weapons, until the skies filled with rockets that flew without crews, until the mathematical certainty of death met the mathematical certainty of the proximity fuse's kill radius. The revolution was coming. The Axis just didn't know it yet. Part 3. Baptism by Fire. The proximity fuse entered combat not with dramatic announcement, but with bureaucratic caution. January 1943, Solomon Islands. The USS Helena fired the first combat rounds during a Japanese air raid. 5 enemy aircraft attacked. 4 fell. The ship's gun crews looked at each other in stunned silence. The new shells performed exactly as promised, perhaps better. But it was in the skies over England 15 months later that the weapon revealed its true revolutionary nature. June 13, 1944. 1 week after D-Day, Hitler unleashed his Vergeltungswaffe, revenge weapon. The V-1 flying bomb, essentially a pilotless aircraft packed with 1,270 pounds of high explosive, began falling on London. The British called them buzz bombs or doodlebugs, nicknames that couldn't disguise the terror they inspired. You heard the distinctive pulse jet engine, a harsh mechanical stuttering, then silence as the fuel ran out, then explosion as gravity delivered the payload. The V-1 flew at 400 miles per hour at altitudes between 2,000 and 3,000 feet. Too fast for most anti-aircraft tracking, too high for small arms, too small and too numerous to stop with fighter aircraft alone. Traditional anti-aircraft batteries fired frantically, uselessly. The timed fuses couldn't track such speed. By late June, the Germans were launching more than 100 V-1s daily at London. The mathematics were simple. If even 20% got through, that meant 20 tons of explosives landing on civilians every single day. Then the Americans supplied their British allies with proximity-fused shells for their 90 mm anti-aircraft guns. The numbers shifted so dramatically that German intelligence initially refused to believe them. In the first week of proximity fuse deployment, British batteries along the coast achieved a 24% kill rate against V-1s. 1 month later, 46%. By August 1944, 74%. Entire waves of V-1s disappeared before reaching London, cut down by shells that required no careful aiming, no split-second timing, just proximity to their target. Gunner William Hartley, stationed at a battery near Dover, described his first proximity fuse engagement with the reverence of someone witnessing something beyond his training. The buzz bomb came over fast, maybe 400 miles per hour, descending toward the city. We'd been missing these bastards for weeks. You'd shoot where they were going to be, but by the time your shell reached that altitude, they'd already passed. This time the lieutenant said we had the new ammunition, the secret stuff from America. We loaded. We tracked. We fired 3 rounds. The second one, I swear it wasn't a direct hit, exploded maybe 40 feet to the left. Just proximity. The blast caught the bomb mid-flight, and you could see it tumble, the wing shearing off, and it crashed into the channel. We stood there, staring. "Do that again," the lieutenant said, so we did. And again. We shot down 7 that afternoon. 7. Before the proximity fuses, we'd consider ourselves lucky to hit 2 in a week. The psychological impact on the V-1 crews in France was immediate and devastating. They'd been told their weapon was unstoppable, that British defenses were overwhelmed. Now their bombs were falling into the English Channel or exploding in empty fields. Launch crews began to doubt. Some requested transfers. The weapon that was supposed to break British morale was itself being broken by American technology. But the Pacific Theater provided the proximity fuse's most dramatic vindication, because there the enemy wasn't a mindless robot. It was human pilots conducting suicide attacks with a fanaticism that defied Western understanding. Butterugger Part 4. The Divine Wind Meets American Science, October 25, 1944. The Battle of Leyte Gulf. Vice Admiral Takejiro Onishi stood on the airfield at Mabalacat, watching his pilots prepare for a mission from which none would return. The war was lost. He knew this with the cold certainty of a professional military man. Japan's fleet was shattered. Its air force was decimated. Its industrial capacity couldn't match the American production juggernaut that was turning out ships faster than Japan could sink them, aircraft faster than Japan could shoot them down. Conventional tactics had failed. So Onishi proposed the unconventional, Tokubetsu Kogekitai, special attack units. Pilots would deliberately crash explosive-laden aircraft into American ships. One pilot, one plane, one ship. The mathematics seemed favorable, even elegant in their brutality. Building aircraft was cheaper than building carriers. Training pilots for a one-way mission took less time than training them for sustained combat. And the psychological impact on the Americans, watching young men deliberately crash into them, might break their will to continue. The first kamikaze attack stunned American commanders. The USS St. Louis, an escort carrier, took a direct hit from a diving Zero. The ship sank in less than an hour, taking 143 sailors with it. More attacks followed. The Americans were facing an enemy that couldn't be deterred, couldn't be frightened away, couldn't be dissuaded by the prospect of death, because death was the mission. Traditional anti-aircraft fire proved inadequate. You could hit a kamikaze, shred its wings, kill its pilot, and its momentum would still carry it into your ship. Close wasn't good enough. You needed to destroy the aircraft completely, to knock it from the sky far enough away that its burning wreckage wouldn't reach your vessel. Enter the proximity fuse. The weapon designed to destroy German bombers over Europe found its perfect application against Japanese kamikazes. Unlike conventional anti-aircraft fire that required direct hits, proximity-fused shells created lethal zones in the sky. A kamikaze diving at 300 miles per hour, the pilot chanting prayers or poems or the names of loved ones would fly into an invisible sphere of death. The shell wouldn't wait for contact. It would sense the approaching metal, the reflected radio waves, and detonate when the mathematics said the fragmentation would be most lethal. The statistics were brutal in their effectiveness. In the latter stages of the Okinawa campaign, American ships equipped with proximity fuses achieved kill rates exceeding 50% against kamikaze aircraft, meaning 1 out of every 2 suicide planes was destroyed before reaching its target. Given that American battle groups could fire hundreds of shells per minute, a single diving aircraft might face a dozen proximity-fused rounds, each one creating its own lethal bubble in the air. Seaman First Class Robert Chen aboard the destroyer USS Laffey survived one of the war's most intense kamikaze attacks. 22 separate aircraft attacked his ship over 80 minutes on April 16, 1945. His account, recorded decades later, still carried the bewildered tone of a man who'd witnessed something he couldn't quite process. They kept coming, wave after wave. We fired everything. 5-inch guns, 40 millimeter, 20 millimeters, even rifles when they got close enough. The proximity shells. That's what saved us. You'd see a plane diving and our 5-inch would fire, and the shell would just go off near it. Not a direct hit, but close enough. The plane would shudder like it hit a wall, then break apart. One came so close I could see the pilot's face, young kid, maybe 19, 20. Our gun fired. The shell exploded maybe 50 feet from the plane. The blast pushed it sideways and it crashed into the water 10 feet from our hull. Close enough I felt the spray, but we survived. 89 other ships at Okinawa went down. We survived because of those shells that thought for themselves. The Laffey took 6 direct hits and 4 bomb strikes but remained afloat. Of its 336-man crew, 32 died and 71 were wounded. Without proximity fuses, naval analysts estimated the ship would have been destroyed within the first 20 minutes of the attack. The kamikazes kept coming, 1,165 attacks at Okinawa alone, but the mathematics had shifted. Each American ship had become a floating fortress protected by an invisible dome of automated death. The divine wind met American science, and science prevailed through the cold logic of physics, optimal detonation distance, fragmentation patterns, kill probability curves. Japanese commanders noticed the change. Attack debriefings, those rare occasions when pilots survived to report, mentioned new defensive fire that seemed to explode without direct hits. Some pilots believed the Americans had developed magnetic bombs that sensed aircraft. Others thought it was advanced radar-directed gunnery. The truth, that each shell carried its own miniature radar system, seemed too advanced, too expensive, too impossible to mass produce. They couldn't imagine the industrial capacity that allowed America to manufacture 22 million proximity fuses between 1943 and 1945. 22 million tiny radar sets, each one more sophisticated than any complete radar system Japan had deployed. The numbers themselves were obscene, revealing an industrial and technological gap that no amount of courage or sacrifice could bridge. Part 5. The German Discovery. The Allied paranoia about the proximity fuse falling into enemy hands wasn't mere caution. It was founded on the knowledge that a single intact specimen could reveal years of research. The security protocols were absolute. Use them only over water or in areas certain to remain under Allied control. Demolition teams followed advancing troops specifically to destroy any duds before the enemy could examine them. Despite these precautions, the Germans eventually captured several intact proximity fuses. The circumstances varied. A dude that landed on a controlled beach, fragments recovered from a downed V-1, a complete shell that failed to detonate. German intelligence operatives delivered them to laboratories in Berlin and Peenemünde, where the Reich's best scientists gathered to reverse engineer the weapon that was destroying their aircraft. Dr. Herbert Wagner, one of Germany's leading missile engineers, led the analysis. His initial examination notes, recovered after the war, reveal a progression from confidence to confusion to something approaching despair. First examination suggests a radio-based proximity trigger, likely similar to our own experimental designs. Confident we can reproduce the mechanism within 6 months. 2 weeks later. The miniaturization is extraordinary. Components we believe would require substantial space are reduced to impossible scales. The vacuum tubes survive firing acceleration through methods we cannot immediately determine. Manufacturing complexity appears extreme. 1 month later. We have successfully mapped the circuit design. The elegance is remarkable, perhaps too remarkable. This represents not mere refinement of existing technology, but a fundamental leap in miniaturized electronics. The Americans have essentially created a miniature radar system that functions reliably under conditions we would consider destructive to such delicate mechanisms. The manufacturing precision required suggests production capabilities we had not attributed to American industry. Reproduction would require retooling entire manufacturing sectors. Timeline, uncertain. The final assessment written in March 1945 as the Reich crumbled. The proximity fuse represents technology approximately 25 years ahead of our current capabilities, not because the principles are unknown, but because the manufacturing precision, miniaturization, and quality control necessary for mass production exist only in American factories. We could build one, perhaps 10, given unlimited resources and time. They have built millions. This is not an achievement of invention alone, but of industrial capacity we cannot match. The war is lost not only militarily, but technologically. Wagner wasn't wrong. Germany had brilliant scientists, innovative engineers, and sophisticated theoretical understanding of radio proximity triggers. What they lacked was the industrial ecosystem that made the proximity fuse possible. Precision machining to tolerances measured in 10,000ths of an inch, quality control systems that rejected components with microscopic flaws, production lines that stamped out components with identical specifications hour after hour, day after day. The Germans did attempt production of their own proximity fuse. By April 1945, they'd manufactured approximately 70 functional prototypes, sophisticated devices that worked reliably in testing. 70. In the same period, American factories produced 1.2 million proximity fuses. The disparity wasn't just numerical, it was civilizational. One nation could turn cutting-edge technology into a mass-produced commodity. The other could only create expensive handcrafted specimens. The Japanese never came close. When American forces overran Japanese research facilities after the surrender, they found evidence of theoretical work on proximity fuses, but nothing approaching functional prototypes. The gap wasn't merely years, it was fundamental, representing differences in industrial development, manufacturing philosophy, and technological infrastructure that no amount of wartime desperation could bridge. Part 6. The numbers tell their story. By war's end, the proximity fuse's impact could be measured with brutal precision. Statistics, cold and absolute, revealed what had changed. Against aircraft. Pre-proximity fuse, 2,500 anti-aircraft rounds required per kill. Post-proximity fuse, 100 rounds required per kill. Improvement factor, 25x against V-1 flying bombs. June 1944, conventional fuses, 24% interception rate. August 1944, proximity fuses, 74% interception rate. V-1s destroyed by proximity fused shells, 2,200 plus against kamikaze attacks. Estimated kamikaze aircraft destroyed by proximity fuses, 350 plus, American ships saved from sinking. Estimated 200 plus, American lives saved. Estimated 8,000 plus. Production statistics. Total proximity fuses manufactured 1942-1945, 22 million units. Peak monthly production 500,000 units. Cost per fuse 1945, $18. Total program cost $1 billion, approximately $17 billion in 2025 dollars. But beyond statistics lay something harder to quantify, the psychological impact of facing a weapon that seemed to think, to hunt, to anticipate. Luftwaffe pilots began avoiding predicted altitudes, knowing American anti-aircraft fire had become unnervingly accurate. Kamikaze pilots faced not just death, which they'd accepted, but annihilation before completing their mission, their sacrifice rendered meaningless by shells that detonated in mid-air. V-1 launch crews watched their weapons, supposed instruments of terror against defenseless civilians, get systematically destroyed by defensive fire that seemed impossible to evade. The proximity fuse changed aerial warfare from a game of chance into a game of mathematics. And mathematics, paired with American industrial capacity, was a game the Axis couldn't win. Söderföraren Part 7. The Secret That Changed Secrets. In November 1944, with Allied victory increasingly certain, the combined chiefs of staff made a controversial decision. They authorized the use of proximity fuses for ground combat during the Battle of the Bulge. The rationale was simple. Germany's surprise offensive had created a crisis severe enough that revealing the technology was worth the tactical advantage. On December 16, 1944, German forces launched their last major offensive in the West. They achieved initial surprise, pushing American forces back, creating chaos in the Ardennes forest. American artillery batteries, receiving emergency orders, began firing proximity-fused shells against ground targets for the first time. The effect was devastating. Traditional artillery shells buried themselves in the ground before exploding, their force largely absorbed by dirt and snow. Proximity fuse detonated the shells in mid-air, 20 feet above German positions, creating air bursts that scattered shrapnel over wide areas. Soldiers in foxholes, protected from ground bursts, found themselves exposed to metal fragments raining from above. Casualties spiked. German commanders reported new American artillery with extraordinary effectiveness. Lieutenant Hans Müller, captured near Bastogne, described the experience in his prisoner interrogation. "We'd faced American artillery before. You could hide, dig deep, and survive most barrages. This was different. The shells exploded above us, not in the ground. The fragments came down like steel rain. Nowhere was safe. Men in deep foxholes were wounded. Men behind cover were killed. We thought perhaps they had new observation aircraft, directing every shot precisely. We didn't understand it was the shells themselves, deciding when to explode." The proximity fuse's effectiveness on the ground, while substantial, paled compared to its anti-aircraft applications. In the air, the three-dimensional nature of combat meant proximity detonation created lethal spheres around fast-moving targets. On the ground, terrain and obstacles limited its advantages. But the decision to use the fuses on land revealed something significant. American commanders believed they had such overwhelming technological superiority that revealing their secret weapon no longer posed a strategic risk. They were correct. German scientists who examined the duds from the bulge confirmed what they'd already concluded from other specimens. The technology was reproducible in theory, but impossible for Germany to manufacture at scale with the war nearing its end. The secret was out, but it no longer mattered. The industrial and technological gap had grown too wide to bridge. Party 8. The Scientists Who Changed War. After Germany's surrender, American technical teams raced across occupied territory, gathering intelligence on German weapons development. They found ambitious projects, jet aircraft, guided missiles, even early designs for intercontinental ballistic missiles. The technological sophistication was impressive, sometimes unsettling. But what struck investigators was what they didn't find. Any German proximity fuse program that approached functional mass production. The Germans had the theoretical knowledge. They lacked the manufacturing ecosystem. Merle Tuve, the physicist who'd led the initial proximity fuse development, reflected on this disparity in a 1946 lecture at MIT. We didn't invent radio. We didn't invent radar. We didn't invent vacuum tubes. Every component of the proximity fuse existed in some form before the war. What we invented was a system, a way of manufacturing precise, reliable, miniaturized electronics at a scale never attempted. We built factories that could produce components to tolerances previously reserved for laboratory instruments. We trained workers to assemble devices with dozens of critical parts, and we did it so well that fewer than 1 in 1,000 fuses failed. That wasn't scientific genius. That was American industrial capacity applied to the problem of turning advanced technology into a reliable, affordable weapon. The proximity fuse program employed at its peak more than 30,000 workers across multiple manufacturing facilities. Unlike the Manhattan Project's handful of sites, proximity fuse production was distributed across America. National Carbon Company in Cleveland manufactured batteries. Wurlitzer, the jukebox company, produced generators. Eastman Kodak and RCA made vacuum tubes. Dozens of subcontractors supplied components, often without knowing their purpose. This decentralization served both security and production efficiency. No single factory could be bombed to halt production. No single worker knew enough to compromise the design. And the system's robustness meant that when demand spiked, as it did during kamikaze campaigns, production could increase rapidly without sacrificing quality. The scientists involved rarely received public recognition during their lifetimes. Merle Tuve died in 1982, his role in developing the proximity fuse largely unknown outside scientific circles. James Van Allen became famous for discovering radiation belts, not for his wartime work. Harry Diamond's miniaturized vacuum tubes made the proximity fuse possible, but his name appears in no history textbooks. This anonymity was deliberate. The fuse remained classified until 1950, and even after declassification, the government discouraged publicity. The technology had evolved into guided missiles, surface-to-air weapons, and other systems that formed the backbone of Cold War defense. Revealing how the proximity fuse worked meant revealing underlying principles that informed an entire generation of weapons development. Part 9. The Weapon That Kept Killing. The proximity fuse's story didn't end in 1945. The technology, refined and improved, formed the basis for virtually every modern guided weapon. Surface-to-air missiles use proximity fuses to destroy aircraft without direct hits. Anti-ballistic missile systems employ the same principles to intercept warheads. Even non-military applications, automobile crash sensors, automated parking systems, collision avoidance radar, trace their lineage to those miniature radio transmitters that fit inside 5-inch shells. But the immediate post-war period revealed an uncomfortable truth. The weapon designed to save American lives didn't distinguish between combatants and civilians when repurposed. In Korea, proximity-fused artillery shells created the same devastating airbursts that had saved American soldiers in the Bulge. In Vietnam, they killed with the same mathematical efficiency. The technology was neutral, only the targets changed. Veterans of proximity fuse development grappled with this legacy. Some, like Tuve, became advocates for arms control, arguing that the same scientific ingenuity that created devastating weapons should be applied to preventing war. Others defended their work as necessary, pointing out that proximity fuses had saved countless Allied lives and shortened the war. The moral calculus remains complex. The proximity fuse killed tens of thousands of Axis personnel, German pilots, Japanese kamikazes, soldiers in the Bulge. It prevented V-1s from striking London neighborhoods. It saved American ships from kamikaze attacks. And it demonstrated that modern warfare had entered a new phase, where electronic intelligence built into weapons could make split-second decisions that once required human judgment. Admiral Ralph Ofstie, in a 1946 Naval Institute paper, captured this transformation. The proximity fuse represents a philosophical shift in how we wage war. We've created a weapon that observes, decides, and acts without human intervention, all in fractions of a second. We've automated killing to a degree previously impossible. This efficiency saved American lives in 1944 and 1945. But we should not deceive ourselves about what we've created, a template for warfare where human judgment becomes increasingly remote from the act of destruction. His concerns would prove prescient as weapons technology continued evolving, eventually producing the autonomous systems and artificial intelligence applications that define modern military operations. Part X, The Germans Who Understood. Too late after the war, American intelligence officers interrogated hundreds of German scientists and engineers, seeking to understand why Germany, despite its scientific sophistication, had failed to develop comparable weapons. The answers revealed a pattern of systemic failures that went beyond the proximity fuse to illuminate why Germany lost the technological race. Professor Werner Osenberg, who'd coordinated German weapons research, was brutally honest in his assessment. We were seduced by the spectacular. Jet aircraft, rocket missiles, super heavy tanks, these captured Hitler's imagination and received funding. The proximity fuse was invisible, unglamorous, an incremental improvement to existing weapons. By the time we recognized its significance, we lacked the industrial capacity to respond. America didn't just build better weapons, they built better systems for producing weapons. That's the war we lost. The disparity extended beyond proximity fuses. German engineers had developed world-leading jet engines, guided missiles, and rocket technology, but struggled to produce them in meaningful quantities. American factories, meanwhile, turned out proven designs, proximity fuses, B-24 bombers, M4 Sherman tanks, by the thousands. Quality versus quantity, sophistication versus reliability, innovation versus mass production. Germany chose innovation. America chose mass production. The results were decisive. German prisoner of war Werner Braun, a radar engineer who'd examined captured proximity fuse, expressed what many German scientists felt. When we saw the complexity they'd achieved, the miniaturization, the reliability, we knew the war was over. Not because of one weapon, but because that weapon revealed a level of industrial precision we couldn't match. They weren't just better engineers. They had better factories, better quality control, better training systems. They'd turned advanced technology into a commodity. We could never do that, no matter how clever our scientists. This technological gap would shape the post-war world. The scientists who developed the proximity fuse, who'd mastered miniaturization and mass production of sophisticated electronics, formed the nucleus of America's aerospace and defense industry. The techniques refined for producing reliable fuse under wartime pressure became the foundation for the electronics revolution, transistors, integrated circuits, microprocessors. The proximity fuse was never just a weapon, it was proof of concept for a new way of manufacturing, a demonstration that complicated electronic systems could be made reliable, affordable, and mass-producible. That lesson, learned under the pressure of war, would reshape the global economy for the next half-century. The Yidrithurasen, Part Int. The veterans who rarely spoke. Joseph Martinez survived the war. The Navy gunner, 23 years old when he first fired proximity-fused rounds from the USS Enterprise, lived until 2012. In all those years, he rarely discussed what the new ammunition meant, what it felt like to watch aircraft disintegrate from shells that seemed to predict their presence. Late in life, interviewed for a World War II oral history project, he tried to explain. "We didn't think about the science. You don't when you're firing for your life. But afterwards, when it was quiet, you'd realize those shells were smart. Smarter than a good gunner, smarter than the best officer with the best calculations. They knew something we couldn't know, the exact instant to explode for maximum effect. It made us feel, I don't know, powerful, yes, but also replaceable. If a shell could make those decisions, what did that mean for us?" His discomfort touched on something deeper than gratitude for a life-saving technology. The proximity fuse represented automation of decisions previously requiring human judgment. It was a glimpse of warfare's future, one where human agency gradually yielded to mechanical precision, where algorithms replaced intuition, where warfare became increasingly abstract. Kamikaze survivors, those few Japanese pilots who survived proximity-fused defenses through mechanical failure or pilot skill, rarely discussed their experiences publicly. Shame, trauma, and cultural factors limited their testimony. But private accounts reveal their bewilderment at defenses that seemed to anticipate their approach, that created walls of explosions in empty air, that destroyed aircraft before impact could validate their sacrifice. One former pilot, Haruo Araki, wrote decades later in a private memoir, "We were trained to accept death. We were prepared for American fighters, for anti-aircraft fire, for collision with steel decks. We weren't prepared for shells that seemed to know we were coming, that exploded without direct hits, that turned our dives into fireballs before we reached our targets. Some of us believed the Americans had developed supernatural weapons. Others thought we'd angered the gods. The truth, that they'd simply built better machines, was somehow harder to accept." The psychological dimension of the proximity fuse is often overlooked in technical histories. But for those who faced it, the weapon represented something unprecedented, automated intelligence that hunted humans with mechanical precision. It was a preview of modern warfare's trajectory, where drones and missiles and autonomous systems would eventually dominate the battlefield, where the distance between decision and death would grow ever wider. Part 13. The mathematics of survival numbers tell stories that words cannot. Consider these. In the Okinawa campaign, 34 American ships were sunk by kamikazes and 368 were damaged. Without proximity fuses, naval analysts estimated those numbers would have been 89 ships sunk and 615 damaged. The difference, 55 ships that stayed afloat, approximately 8,200 sailors who survived. Each one a son, a brother, a husband, a father who came home because a miniature radar system detonated a shell 40 feet from an incoming aircraft instead of waiting for contact that would never come. In England, the V1 campaign launched approximately 10,500 flying bombs at London between June 1944 and March 1945. Without proximity fuses, British analysts calculated that roughly 6,800 would have reached the city. With proximity fuse, only 2,400 got through. The difference, 4,400 bombs that exploded over empty fields or fell into the channel. At 1,870 pounds of explosive per bomb, that's 8.2 million pounds of explosives that never reach civilian targets. At an average of 7 casualties per V1 impact, that's approximately 30,000 British civilians who lived because American factories could mass-produce sophisticated electronics. But numbers also obscure. They transform individuals into statistics, deaths into data points, suffering into calculations. Each V1 that did reach London killed real people in real homes. Each kamikaze that penetrated the proximity fuse defense screen destroyed real ships with real crews. The weapon saved lives. It didn't eliminate death. Commander Eugene Fluckey, who earned the Medal of Honor for submarine operations in the Pacific, observed something crucial in his 1947 memoirs. The proximity fuse gave us a tremendous advantage, yes. But it didn't make us invincible. It changed the odds. It tilted the mathematics of survival in our favor. War remained war, brutal, random, unforgiving. We just had better tools for staying alive long enough to finish the job. This pragmatic assessment cuts through both triumphalism and guilt. The proximity fuse was a tool, sophisticated and revolutionary, but still just a tool wielded by humans in pursuit of very human goals: survival, victory, the desire to return home. Its significance lies not in moral judgment, but in what it revealed about industrial modernity's capacity to turn scientific principles into mass-produced weapons with startling speed. From concept to deployment, 3 years. From initial production to 22 million units, 3 years. The velocity of innovation driven by existential threat and unlimited resources demonstrated what was possible when a wealthy, industrialized nation focused its entire capacity on a single problem. That lesson, the power of coordinated industrial mobilization, would shape Cold War military development, space programs, and civilian technology for decades. Part 15. The technology that couldn't be shared in 1946, with the war concluded and wartime alliances fracturing, American military planners faced a delicate question: what to do about proximity fuse technology now that former allies were becoming potential adversaries? The Soviet Union, nominally an ally during the war, had received virtually no information about the proximity fuse, despite receiving extensive other military aid through Lend-Lease. The secrecy wasn't accidental. American intelligence knew Soviet agents had penetrated the Manhattan Project, and they suspected similar efforts targeted other advanced weapons programs. Proximity fuse technology, with its applications to guided missiles and air defense, was deemed too sensitive to share even with wartime partners. This created post-war tensions. Soviet scientists had captured German proximity fuse specimens, and like the Germans before them, recognized the manufacturing challenge more than the theoretical complexity. Soviet industry in 1946 lacked the precision manufacturing capacity for mass production. They could build crude copies and did, but not at the scale or reliability that made the American version strategically significant. The British, who'd received proximity fuse under strict security protocols during the war, found themselves in an awkward position. They understood the technology, had contributed to its refinement, but depended on American production for supply. Post-war, they developed their own manufacturing capability, but the years-long gap reinforced Britain's declining position relative to American technological supremacy. This technological hoarding set a precedent for the Cold War era. Advanced weapons technology became a closely guarded asset, shared only with the most trusted allies and under strict control. The proximity fuse, a weapon that had helped win World War II, became in peacetime a symbol of technological advantage, jealously protected against potential adversaries, including nations that had fought alongside America just months earlier. Dr. Vannevar Bush, who'd coordinated much of America's wartime scientific effort, defended this approach in a 1947 congressional testimony. The proximity fuse represents more than a single weapon. It represents a capability, the ability to miniaturize complex electronics and produce them reliably at scale. That capability underpins our current air defense systems, our guided missiles, our entire approach to modern warfare. Sharing the specific techniques developed during the war would be sharing our fundamental strategic advantage. That's not something we can afford in an uncertain world. His testimony revealed the transformation that had occurred. Scientific knowledge, once shared relatively freely across borders, had become weaponized, classified, restricted. The proximity fuse's legacy extended beyond its direct military applications to reshape how nations thought about technological development itself. Chadjusarm, Part 14, The Accountant's War. Here's a calculation rarely included in proximity fuse histories: return on investment. The program cost $1 billion, a staggering sum in 1940s dollars, equivalent to roughly $17 billion today. That billion dollars produced 22 million fuse at an average cost of $18 each in 1945 dollars. Each fuse improved kill probability by approximately 25 times compared to conventional ammunition. Now the darker mathematics. The program is estimated to have saved 55 American ships from sinking. A Fletcher-class destroyer cost $6 million to build. An Essex-class carrier cost $78 million. If we assume the 55 saved ships averaged $20 million each, conservative given several were carriers, that's $1.1 billion in replacement costs avoided, essentially breaking even on the program cost before counting any other benefits. Then add approximately 8,000 American sailors' lives saved. If we apply the military's own statistical value of life calculations used for benefits and compensation, that's billions more in actuarial savings. Add the British civilian lives saved from V-1 attacks. Add the shortened war duration. Every month of continued conflict cost the United States approximately $8 billion in direct military expenditure. By these cold calculations, the proximity fuse ranks among the most cost-effective weapons programs in military history. $1 billion spent in 1940-1945 returned multiples of that value in saved equipment, saved lives, and shortened conflict. But these calculations reveal something uncomfortable about modern warfare: its reduction to financial optimization, its treatment of human life as an actuarial variable, its transformation into a problem of industrial efficiency rather than human tragedy. The proximity fuse excelled by every metric that matters to defense planners: cost per kill, probability of intercept, production scalability, strategic impact. By metrics that matter to philosophers and moralists, its legacy is more complex. Colonel Paul Tibbets, who piloted the Enola Gay and later commented on various weapons technologies, offered an unsettling observation. The proximity fuse made killing more efficient. That's its purpose, its function, its success metric. We can dress it up in language about saving American lives, and it did save lives. But let's be clear about what we invented: a way to destroy enemy aircraft and personnel more reliably and at lower cost. That's the logic of war. The proximity fuse just executed that logic more effectively than previous technologies. Whether that's progress depends on your perspective. His cynicism cuts through the sanitized language of defensive weapons and force protection to the core function: optimized destruction. The proximity fuse killed better, faster, cheaper than alternatives. By military logic, that made it a triumph. By humanitarian standards, it was a more efficient tool for ending human lives. This tension between military effectiveness and moral complexity defines all weapons technology, but seems especially acute for the proximity fuse because of its automation. The shell didn't hate its targets, didn't experience fear or rage or hesitation. It simply calculated distance and executed its programming with mechanical precision. It was a glimpse of warfare's future: algorithmic, automated, optimized. Part 15. The Secret That Everyone Forgot. By 1960, the proximity fuse had largely faded from public consciousness. Younger Americans knew about the atomic bomb, about D-Day, about famous battles and generals. Few remembered the miniature radar sets that had protected their ships and cities. The technology had been so thoroughly absorbed into standard military practice that its revolutionary nature was forgotten. This amnesia served multiple purposes. The fuse's underlying technologies had evolved into Cold War weapon systems that remained classified. Drawing attention to the proximity fuse meant drawing attention to its descendants: surface-to-air missiles, anti-ballistic missile systems, guided munitions. Better to let the public forget the original while the military refined its successors. But the forgetting also reflected something deeper. The proximity fuse didn't fit comfortable narratives. It wasn't the decisive weapon that ended the war like the atomic bomb. It wasn't attached to heroic individual actions like fighter pilots or infantry assaults. It was industrial, technical, collective, the product of thousands of engineers and workers whose names nobody remembered, creating a weapon that killed through mathematics rather than valor. Harry Diamond died in 1948, his miniaturized vacuum tubes having made the proximity fuse possible. His obituary in the Washington Post ran 3 paragraphs and never mentioned his wartime work, which remained classified. Merle Tuve lived longer, dying in 1982, but his fame came from peacetime contributions to geophysics and scientific administration, not from the weapon that had saved thousands of lives. The proximity fuse's greatest practitioners were similarly forgotten: the gunners who fired it, the sailors who loaded it, the pilots who watched it destroy aircraft approaching their carriers. They became statistics in war records, their individual experiences subsumed into aggregate data about kill rates and interception percentages. Only decades later, when veterans began dying and oral historians raced to capture their stories before they vanished entirely, did individual accounts surface. And even then, the focus often remained on dramatic battles and famous encounters rather than the systematic, technological transformation of anti-aircraft warfare that the proximity fuse represented. In 1976, an aging James Van Allen gave a lecture at the Smithsonian about the proximity fuse program. The audience numbered 47 people. Van Allen, by then famous for discovering the radiation belts around Earth, spoke passionately about his wartime work, about the urgency and innovation and collaboration that had created a revolutionary weapon in 36 months. He showed technical diagrams, test footage, production statistics. The lecture received no press coverage. No newspaper considered it newsworthy. The proximity fuse, once guarded as jealously as the atomic bomb, had become an obscure footnote in World War II histories, remembered mainly by specialists and veterans who'd seen its effects firsthand. This obscurity represents its own kind of success. Technologies that become ubiquitous lose their revolutionary character. The proximity fuse's principles, miniaturized electronics, automated decision-making, sensor-guided weapons, are now so standard that their radical nature is invisible. We live in a world shaped by the innovations forced by wartime necessity, but we've forgotten the journey from impossible to inevitable. Jean-Lapierre, Part 16, The Final Calculation. December 5, 1944, Philippine Sea, 0547 hours. We return to Lieutenant Commander Howard Mitchell on the deck of the USS Lexington, watching Japanese aircraft fall from the sky with an efficiency that defied his training, his experience, his understanding of what was possible in aerial combat. In that moment, he couldn't know he was witnessing the future. He couldn't know that the miniature radar sets packed into 5-inch shells represented a template for warfare that would dominate the next 70 years. He couldn't know that the same principles would guide missiles from ships, from aircraft, from satellites orbiting 200 miles above the Earth's surface. He knew only that the rules had changed. The old mathematics of aerial combat, the brutal calculus that required thousands of shells to destroy a single aircraft, no longer applied. His gunners could create zones of death in the sky, invisible spheres of radio waves and fragmentation where enemy aircraft simply ceased to exist. The Japanese pilots diving toward his carrier group that morning couldn't know what killed them. They saw shells explode without direct hits, felt their aircraft shudder from blasts that seemed to anticipate their position, and then, for most, nothing. No impact with enemy ships, no heroic sacrifice, just sudden violent disintegration in midair, their missions incomplete, their deaths meaningless by the logic of their own sacrifice. This was the proximity fuse's true revolution. Not merely improved kill rates or better resource efficiency, but the transformation of aerial warfare from an art into a science, from a contest of skill and courage into a mathematical equation that American industry could solve through mass production of miniaturized intelligence. Mitchell survived the war. He returned to California, raised a family, worked in civilian shipping for 30 years, and died in 1991. He rarely spoke about that December morning, about the strange feeling of watching enemy aircraft destroyed by shells that seemed to think for themselves. When he did discuss it, usually after too many drinks at VFW meetings, he would say something that puzzled his listeners. We didn't beat them with courage. We didn't beat them with superior tactics. We beat them with accounting. We could afford to put a tiny radar set in every shell. They couldn't. That's modern war, not who fights harder, but who builds smarter. His bitterness reflected a truth that military historians often obscure. The proximity fuse represented the industrialization and rationalization of killing to a degree previously impossible. It stripped away romance, valor, individual skill, all the qualities that make warfare comprehensible to human psychology, and replaced them with industrial production metrics and kill probability curves. The weapon saved his life. He was grateful for that, but he spent the rest of his years uncomfortable with what it represented: the reduction of warfare to an engineering problem, solved through mass production and superior manufacturing capacity. Heroes weren't needed when you had superior technology mass-produced at scale, just competent operators following procedures, firing weapons that did the thinking themselves. Epilogue: the weapon that never stopped. The proximity fuse as a specific device became obsolete within decades. Transistors replaced vacuum tubes. Solid-state electronics replaced mechanical components. Laser rangefinders and radar tracking systems surpassed the simple radio proximity detection of the original design. But the principle never died. Every guided missile, every smart bomb, every autonomous weapon system traces its lineage to those 5-inch shells that could sense their proximity to targets and act on that information without human intervention. The proximity fuse was the first weapon to automate the decision cycle: observe, orient, decide, act. That cycle, compressed into fractions of a second and executed by electronics rather than human brains, defines modern warfare. In 2025, American defense contractors build weapons with capabilities that would seem like fantasy to the engineers who developed the proximity fuse. Missiles that can identify specific vehicle types and choose optimal impact points. Drones that track targets across continents. Autonomous systems that can engage enemy forces without human authorization, all descendants of the principle proven in 1943 that machines can observe, decide, and kill more efficiently than humans. The proximity fuse was secret weapon number 2 after the atomic bomb. But unlike the atomic bomb, which remains a weapon of last resort, the proximity fuse's descendants are everywhere, on every warship, in every aircraft, at every military installation around the world. Its legacy isn't a single dramatic weapon, but a philosophical transformation: the acceptance that automated systems should make lethal decisions, that human judgment can and should be replaced by algorithmic precision in the business of warfare. The soldiers who fired the first proximity-fused rounds are dead now, almost all of them. The engineers who developed the technology have followed. The factories that produced 22 million fuse have been demolished or repurposed. But the idea persists, evolves, metastasizes into weapons that would astonish their creators with their sophistication, while revealing themselves as natural extensions of principles proven 80 years ago in the skies above the Pacific. The proximity fuse changed warfare once. Its descendants continue changing it still, each iteration pushing human judgment further from the moment of killing, each advancement making warfare more efficient, more precise, and somehow less human. That's the secret that horrified the Axis when they discovered what the Americans had built: not just a better fuse, but a glimpse of warfare's future, where victory belongs not to the bravest or most skilled, but to whoever can build better machines to do the killing. The future where courage matters less than manufacturing capacity, where valor is obsolete compared to superior technology, where war becomes, as Mitchell bitterly observed, a problem of accounting. The proximity fuse won World War II not through any single dramatic moment, but through the steady, inexorable mathematics of industrial warfare. 22 million units, 25 times improved kill rates, thousands of lives saved. Thousands more lives ended with mechanical precision. The Axis was horrified when they saw what it was. They should have been. It revealed a gap not just in technology, but an entire civilization's capacity to mass-produce sophisticated weapons, a gap that couldn't be closed through genius or courage or sacrifice, a gap that meant defeat as surely as any lost battle. And we, living in the world that weapon helped create, should perhaps share some of that horror. Not because the proximity fuse was uniquely terrible, war is terrible, all weapons are terrible, but because it showed us a future we've now fully embraced, where machines make lethal decisions within human efficiency, where warfare becomes increasingly automated and abstract, where the distance between the person who authorizes death and the person who dies grows so wide that moral accountability becomes diffuse, statistical, impossible to locate. The proximity fuse was just a shell with a radio set, but it contained the seed of our present reality, where drones circle overhead and algorithms decide targeting priorities, and warfare happens at digital speed, executed by systems that observe, orient, decide, and act without hesitation, without mercy, without humanity. That was secret weapon number 2, not the atomic bomb's apocalyptic power, but something subtler and perhaps more insidious, the proof that we could make killing efficient, reliable, and automatic. The Axis was horrified. 80 years later, perhaps we should be too.